Good afternoon, everybody. My name is Savio Shankalepore. I am an assistant professor at the Eindhoven University of Technology in the Netherlands. Today, I am presenting you a work carried out together with a master student I supervise, Siva Ganesh Ganti, in collaboration with the Technology Innovation Institute in Abu Dhabi. The name of the work is Selective Authenticated Pilot Location Disclosure for Remote ID-Enabled Drone. This is an agenda of what I'm talking about. First, a little context and motivation for our research. Then I will present the system model, our solution in a nutshell, some security consideration, and some highlights from our extensive performance assessment, to then conclude with conclusions and future work. The context of our research is the one of unmanned aerial vehicles, also known as drones. You probably know that today they are increasingly adopted in several application scenarios, including smart city and search and rescue, for example, and the number of deployed drones is increasing every year, posing concerns also on the regulatory entities that have to arrange the traffic of these drones together, for example, with other flying vehicles like aircraft, and so creating concerns about their tracking and accountability of their operation. To this aim, several aviation authorities, for example, the FAA in 2023 for the US and the EASA for the European Union in 2024, enforced regulations for basically accountability of drone operations. These regulations are called remote identification regulations, and they involve the plain text disclosure of drone information over wireless channels. They can be Wi-Fi or Bluetooth. For the aim of this work, that's Wi-Fi. This information includes drone identity, location, and pilot location, just to name a few of this information. Of course, this information can be sensitive. In particular, in this work, we focus on the pilot location, because especially for commercial operations or for drone flights very close to country borders, the disclosure of the location of the pilot of the drone can be particularly sensitive. The pilot can be immediately localized, and the overall business or the mission of the drone can be threatened through the disclosure of such information. A naive solution to this problem would be to encrypt basically the location shared in the remote ID messages through a shared symmetric key. But this solution has no flexibility. Whenever someone else would like to see the location disclosed by the drone, it needs to have this key. And the problem of key distribution, that is the classical problem of symmetric encryption, will basically prevent any meaningful disclosure of the pilot location in a confidential way. This leads to our main research question. Can we design a protocol for efficient real-time pilot location privacy together with message authentication, that is one of the main requirements for a secure remote ID deployment, in a standalone READ-compliant solution working on board of a drone? This is not a naive question, an easy question to be answered, because there are several challenges and requirements to consider. First, you have to consider that drones are characterized by heterogeneous processing capabilities. We have high-end drones, but also very low-end drones, which has also very limited energy availability, ranging from a max of 30 minutes, but also to a mean of even 7 minutes. So the solution should be very energy friendly. At the same time, since we want a solution that is compliant with remote ID, we have to consider the constraints imposed by remote ID. Remote ID forces drones to broadcast those messages once every second, and static data like the pilot location should be recomputed every 3 seconds. So you disclose it every second and it should change at least every 3 seconds, recomputed. Moreover, remote ID messages should not be fragmented. Otherwise, we have a reliability problem that can affect this broadcast transmission. So the max dimension of every remote ID packet should not exceed 2,304 bytes. That is the MTU of Wi-Fi. To solve this problem, in our paper, in our work, we consider two main building blocks, CPAB and Schnorr signature. CPAB, that is ciphertext attribute-based encryption, it's about the encryption of plain text using an access policy defined over a set of attributes. In brief, receivers can decrypt the ciphertext only if they own an attribute set satisfying the access policy encoded in the disclosed message. There are four phases: setup, keygen, encrypt, and decrypt. And theoretically, this could be a solution that solves the problem of the naive solution, the flexibility. The problem is that CPAB operations typically are costly because they involve pairing operations that are particularly heavy to be executed, specifically on constrained drones. For the signature problem, the building block that we use is Schnorr signatures that are kind of famous in the constrained network application domains because they are compact signatures that can trade off computational complexity with bandwidth requirements. Also, this solution has never been applied in the context of drones, and in particular for broadcast transmission originated by constrained devices. We put everything together and we created a solution that we call SNEL. You can see here the logic of our solution. For the details, you can go on the specific paper. What is here? The drone creates and generates a nonce and encrypts this nonce, that is a random number, using CPAB. We have a ciphertext. We take it for the next phase. Then we take the nonce, the plain text nonce, and we generate a symmetric key starting from the nonce. We use this symmetric key to symmetrically encrypt the pilot location using a symmetric encryption algorithm. This can be, for example, the AES algorithm. Then we sign the all remote ID message, so including not only our encrypted pilot location, but also the other fields using the Schnorr signature scheme. We put everything together and we deliver what we call a secure read message. Any observer that is an entity interested in recovering the message, the contents of the message delivered by the drone, first verifies the Schnorr signature of the message, ensuring the authenticity of the message. Then, to recover the pilot location, it first decrypts the ciphertext using CPAB. This is possible only if you have a set of attributes satisfying the access policy. Using this, you obtain the nonce. You generate the symmetric key through a simple key derivation function, the same used by the drone. You obtain the symmetric key that you need, and then you apply symmetric decryption on the encrypted pilot location that is in the message to recover the pilot location. This is the scheme SNEL that in practice is using a hybrid form of CPAB. This particular technique is also useful for the application of our solution on constrained devices, since all CPAB operations in principle can be pre-computed or can be accelerated offline. That's the property that makes this solution particularly useful for application on constrained devices. First, we verified the security of our solution. We did not do an actual formal analysis using proofs because we were using standard building blocks, but we used a tool that is Proverif that is particularly indicated where you combine building blocks in a way that is new. We proved that our solution is able to achieve pilot location disclosure, robustness to impersonation, and to modification of the message. It can mitigate replay attacks, and we also discuss in the paper the robustness of our solution to birthday attacks and to asynchronous attribute revocation. You can find the code that we implemented for SNEL in Proverif on this link that you can find also in the paper. A significant part of our work was also the performance assessment. We deployed our solution on two relevant devices, two actual drones. The first one is a kind of medium-end drone, the Lumineer QRV Air, that is using in practice as its own core a Raspberry Pi. The second one is a very constrained drone, an ESP32 drone that, as a core, is using the ESP32 microprocessor. The most interesting feature of this microprocessor is the ability to run two separate processors at the same time. For that, we developed three different implementation strategies: fully precomputed, partially precomputed, and parallel computation. In the fully precomputed, we precomputed all the parameters of CPAB. In the partially precomputed, we accelerated the operations to the precomputation of only some parameters. In the parallel computation, we do everything at runtime by using the two cores that are provided by the ESP32. Both implementations are publicly available. These are the links, and you can find them in the paper. There is an extensive performance assessment in the paper. Here, there are some highlights that I want to share with you. First, the picture on the left that is the overhead of the solution by the message overhead, the bandwidth overhead of the solution by increasing the number of attributes in the policy. You remember that we have the constraint that is that we don't want to exceed a single Wi-Fi message. With different curves, the overhead changes slightly, but in any case, we can include in the packet up to a policy with up to 22 attributes. That's particularly efficient, especially for complex scenarios. The other two graphs here show the execution time of our solution and the energy consumption on the most constrained deployment, that is the one on the ESP32. From the graph, from the figure in the middle, you can see that as for the execution time, for all the computation strategies implemented, we are below the limit of 3 seconds. That is the limit imposed by the remote ID regulation. For the energy consumption, especially if you look at the y-axis here on the right, you see that even in the worst case, we consume always less than the 0.0035% of the battery that is included together with ESP32 drone. So our solution, independently from the specific configuration, is also particularly efficient. Just to notice here that as for the execution time, the parallel computed version is the quickest, while for the energy consumption, the parallel computed version consumes a little bit more because you need the energy to run 2 processors at the same time. More details are in the paper. Just to highlight our work, SNAP, that is an integration between CPAB and Schnell Signature for broadcast remote ID. We verified the security of our solution, and we extensively assessed its performance. With the most demanding configuration, we always consume a negligible portion of the battery. In the future, we want to integrate SNAP with other privacy-preserving solutions for other fields of the remote ID message, for example, identity and location disclosure. For any questions, I am here to answer your concerns. Thank you.
So hopefully we have the speaker. Are there any questions? I have one if they're... Are they online? Oh, lovely.
Yeah.
So for the ESP32, were you making sure to use sort of the hardware acceleration capabilities of the chip, and just wondering sort of like what kind of performance difference you might have observed, for example, if maybe your microprocessor doesn't have those capabilities?
Yes, thanks for the question. That's a significant capability that your microprocessor needs to have, because CPAB is notoriously heavy from the computational perspective. So our processors, the ESP32, has a cryptographic accelerator that you can use to speed up computation that we used to speed up computations. Without using the hardware accelerator, there is no way to stay below the limit of 3 seconds. The only way that you have is to fully pre-compute everything. So basically to trade off the computational overhead that you get with some memory overhead. This means that whatever drone that has to implement this solution needs to have a cryptographic accelerator, especially if this solution needs to be used in the other two configurations, the parallel computed on the or the partially pre-computed. That's a requirement for sure.